Okay, so today on the bench, it's kind of obvious what we have. Cobra 2000 GTL. A customer sent this in basically to have its 100,000 mile tune-up, as I call it. So I'll just read off the note here. Let's see. She's in fairly good health, but could be better. The only one you need to know about is the clarifier needs work. There's a switch channel mod connected to the speaker switch. That will go. The counter is a bit dim, but the cap job may improve that enough. Doubtful. Cap job's usually not going to affect the intensity of the... I mean, it's possible, but I doubt that replacing the caps are going to fix a dim display. I'm not going to drive an amp on the radio, so please set the power out to whatever it can do and sound good on AM and SSB without splattering and shortening the life of the radio. So in other words, do a factory transceiver alignment to it and the radio will last for decades. It'll be a happy radio, the way it was designed to be used. Please ignore the power cable mod I did and the power supply filter cap replacement. They should be okay. Remains to be seen. Haven't really looked at the radio yet. Please install a Channel King board with scan and noise toys. I'll never use them, but what the hell. If you think a new 145016 PLL will yield more channel, well, no, he doesn't need to worry about any of that, because when I install the Channel King board, the PLL that's in this radio is going bye-bye anyhow, because it'll get the PLL adapter board. So he doesn't even need to worry about that. If you've done your research on Ranger VCO parts, throw a few of them in there too. If you haven't done your research, feel free to use it. We don't really need to worry about that because of the way the radio is being modified. Capacitor replacement job, including frequency counter caps. Please replace Zener diode and counter. Always do that. Upgrade that to a 1 watt. Please use larger filter caps where you think needed. Heatsink compound, redo if needed. Factory service updates if needed. Now here's where it gets interesting. And this is a new one on me. So this is a mod. He's not sure if it's going to do anything, if it's worth doing. So everybody out there wants to sell you little kits, especially on eBay nowadays. And in shops especially. If you watch my videos, you know how many mods I remove. That's what I spend most of my days doing, is removing crap. It's because shops, well, rightfully so, they're a shop. They want your money. That's how we, the repair industry, make money, is by doing work to radios. But we shouldn't be doing work to radios that's unneeded or causes actual degradation in performance instead of an increase. So one popular modification out there is the receive mod. In a radio like this, it would normally be called a 5-piece. So there's four Schottky diodes that would be installed in the first RF amplifier transistor. But this one was a little different. It's a 5-piece. It's right here. He actually sent it. It was taped to the paper. It says, if you think the Schottky diode and 2SC1730L first amp transistor job is worth the effort, I have included them. So that kind of got my curiosity piqued. 2SC1730L. I don't keep up on this crap. All this bullshit you see, pardon my French, but people always, trying to mod their radios for better performance. These are good radios out of the box. Just get a good alignment done to it, and they're amazing receivers. But everybody's always trying to squeeze out that last little bit. So that got my interest. It's not a 2SC2999. That's the normal modification. And then I also noticed the diodes are different. These are not the normal... I'd have to find the drawer where I've got them. Matter of fact, there they are. Just pull out some. I've got thousands of these. Got a whole reel of them. But this is what you'll normally see. The little blue Schottky diodes will be installed. You stick 4 of these in there and a 2SC2999. None of those parts are in this bag. This is that 1730, and the diodes were, what are they? BAT85s. So I actually need to pull that up. They may be Schottky diodes, but I want to pull up the data sheet on those and just to see exactly what they are. So if you do not, there are 5 new parts for your collection. So What he says is, may I suggest you do the job, video it, and prove once and for all if it works on a generic Cobra 2000 or not. That would be a popular YouTube video. If you know any other 2000 GTL magic parts replacements, please do them. I trust your judgment, blah, 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 blah. So yeah, that's pretty much it. So here's what I want to do. I've tried that receive mod before, and the juice ain't worth the squeezing, people. It's just a way, it's just something to sell you, to get money. A couple cents in parts, well, actually, I guess they make a couple dollars in parts, even though there's only a couple cents there. And the time to put them in. You know, but it's just more stuff to add to your bill when they do stuff like that. So here's what I want to do. So like he said, could you settle it once and for all? Now, granted, it doesn't matter who, if I do the mod, 50 other shops could do the mod and post the actual test showing it being done, and people still wouldn't believe it and they'll still argue about it, but I'm going to do it anyhow. So, but I'll show what we're going to do is, and I'm actually going to do it 3 different ways. I'm not just going to use these, because like I say, this one's kind of a new one to me. Different diodes, different transistor. So what I want to do is, I'm going to recap the rate, basically restore it to factory condition. So it will not have any modifications, other than if the clarifier is already unlocked, but that wouldn't affect receiver's performance. But I'll replace the electrolytic caps, you know, fresh heatsink compound on all the parts, all the normal work I'd do, but I'm not going to put the channel cane board in yet. I'll basically put it back to a stock condition, and we're going to take some measurements. We're going to take, let's see, we can do a synad measurement. We'll do THD, or total harmonic distortion. We'll do total THD plus noise. What else could we do? I guess we could also try doing adjacent channel. So we could test the receiver's ability to reject adjacent channel splatter. So adjacent channel rejection is what we'll be measuring. But what I want to do is test the stock radio. We're then going to put these 5 parts in. Then we're going to run that same set of tests again under the exact same conditions. Then I'm going to pull these parts out, and I'm going to put in what most people are familiar with. The normal Schottky diode mod and a 2SC2999 transistor. So we'll compare the difference, if there is any, between doing the normal kits that at least I've seen in the past, this new kit that's apparently out there now, and we'll compare that to a bone stock radio. Take some measurements and see, is it worth a shit? Does it really improve anything? Now, I can guarantee you there is going to be a measurable difference. There always is. Anytime you do anything to a radio, there's going to be some type of change. Anytime you change any part in this radio with a different part, you're going to change something, and there's going to be a quantitative measurement that you can take to show a difference. The problem is most of those modifications, how should I put this? The level of improvement may be measurable on an instrument, but it's not perceivable by the human ear. Our ears, quite honestly, are horrible. Human beings have absolutely horrendous hearing. We have probably on the planet, when it comes to mammals, we have some of the worst hearing there is. So, but those levels that a lot of times you can attain by changing parts, yeah, there's an improvement, and that's why I call it the juice ain't worth the squeezing. It's there. There is an improvement, but you're never going to hear it. And a lot of times people put those parts in and they say, oh my God, the radio's so much better. No, actually it's probably not. It's perceived. That's another problem with human beings is our brains. Our brains are really good at tricking us. And they've proven this before. All you have to do is invest money in something, be it a couple cents or dollars in parts or thousands or tens or hundreds of thousands of dollars. But once you've got skin in the game, you've invested your life into that. Your brain, even though it may decrease performance or there may not be a change at all, your brain will still try to trick you into thinking that actually there is, because it's trying to convince you that what you did was worth it, that you didn't make a foolish error by doing something. So, like I say, we'll test it out and we'll see what the results are. So, let's have a look-see at what we got here in the box. Now, I had told this customer I didn't need the covers or anything. That's kind of just because this thing came all the way from California, so it had to come the whole way across the country. So that's that's a lot of extra weight, shipping weight that he really didn't need to send. I don't need covers. So, okay, well, I see the mod that he's talking about. He put an IEC power cord jack in it. Why is there a big nut in the box? Shredded paper. I hate shredded paper. So let's get this out of the way and have a look-see at this guy. Okay. So yes, looks like all original electrolytic capacitors. I can see, where's my pointy stick? Still have a lot of corrosive glue in here, so we'll get all that crap taken out. Like I say, the PLLs, that PLL is going bye-bye anyhow. I can see the glue's been broken there. We have glue all over the place here. We'll get that taken out. Where in the hell is the crystal? What? What? Oh, did he say there was a channel mod? Eee, what is that? There's a circuit board down in there at the front of the radio that ain't supposed to be there. So I'm assuming it's got a homemade, kind of like a, what the hell were those old crystal switchboards you could get for upper and lower channels. That's probably what that is. So yeah, that'll be going bye-bye. Because like I say, it's going to be getting the Channel King board. Now what I'll do is I'll remove all of that, put the original because I'm going to need the original factory crystal there anyhow. I'll take all that, I'll remove that modification, put it back to a factory stock condition to do our testing. But yeah, well, it looks good. Yeah, camera's always in the way. It's hard for me to get my head down in there past the camera. I don't know, if it doesn't really look like any limiters are snipped. Or is it? Yeah, it is. It's missing. So that'll have to be... We can see there's empty holes. Transistors missing, so yeah, have to put that back in. So that means this thing is has horribly distorted transmit. Get the cover off here. Doesn't look like the counter's ever been boogered with, other than somebody did install a diode here. So I don't even need to plug it in. I know this has a seconds display, because that's what that diode does. Cobra was kind enough to put the holes there, and they even have it on the factory schematic. It even shows clock or seconds. But yeah, you install that diode there, and that adds the seconds to your clock then. So top side doesn't look really bad. Like I say, it's got some glue. I'll flip the radio over here and we'll see exactly what the heck this modification is. But in general, we're looking pretty good. And like I say, these received modifications and all this other crap. Honestly, people, the old saying, if it sounds too good to be true, it probably is, couldn't be more true when it comes to CB mods. If a mod sounds too good to be true, it probably is. Ooh, well, he actually went all out. He didn't just stick an IEC connector in, he stuck in a filtered one, EMI filtered assembly. So this actually has some built-in filtering internal, and actually it even has the schematic written on top of it. But yeah, he stuck in a filtered adapter there. Ooh, I don't like that. See that? Those wires are all pinched in there. So 120 volt comes in, goes to this board, and then comes back out this board. So this is still 120 volts AC on these two lines, and goes up to the power transformer to be reduced down. We're going to have to do something about that. I'm going to have to pull this module out, and at least, because that's a pass-through, there's a little grommet right there, a little plastic pass-through, that at least needs to be snipped down a little bit, because like I said, that could pinch through, and then that's going to short out either the hot or the neutral to the metal case on this thing, which is the chassis. So yeah, we don't want that, so that has to be fixed. That's a big safety problem there. Terminals, everything, nice tight terminals. This thing's kind of floating up in the air. Actually, what this should have is a standoff. It's going to be sitting like this. This needs to be raised up a little bit. It's kind of hard to see in the camera, but the board is bowed up. It's bent. So that needs to be fixed up a little bit better. And then we have our crystals. So yeah, basically what I assumed it was going to have. The factory crystal's been located here with a trimmer capacitor. So whoever did this at least did put trimmer capacitors in here, so the frequency could be adjusted for all three of these. So this is the factory one, and then what the mod will do, and I think he said it was what the speaker switch. So depending what position you have the speaker switch in, it's either going to select this crystal, or this crystal. So usually it's going to be, factory 40, 40 upper channels and 40 lower channels. I don't like these type of modifications because of this right here. See that? That's wire. It's a floppy piece of wire that can move around. You've got wires that run from here up to the switch, wires that run from that switch back to the board. All of these wires, the slightest bit of movement of these wires is going to change the capacitance in that circuit, which changing the capacitance to these crystals is going to change the oscillating frequency. So you end up with an unstable frequency, and your frequency will, you can, especially on sideband, if you end up playing, you're always turning the clarifier, trying to clarify people in, it's because of crap like this. This is horrible for frequency stability. So that's why I do not like these channel switch modifications like this with crystals, with all these long wires with varying inductance and capacitance. So like I say, this is going to have to go back to factory anyhow for the Channel King board. So yeah, what I'll do is put this crystal back where it's supposed to be, just take all this crap out, hook the speaker switches back up the way they're supposed to be, and that'll be good to go then. Why do we have a monster? That's completely unnecessary. Look at the size of the wire used for the antenna. Sweet Jesus, what is that? 14 gauge wire, or some, maybe even 12. Ooh, trust me, this radio will never make anywhere close to enough power to need a wire that big, but it ain't hurting nothing. There is a resistor missing, so I'll have to check all that out. But yeah, otherwise it doesn't look bad. Because they did that switch mod with crystals, they didn't have to cut any traces, so this is completely untouched over here, which is nice to see. Yep. So let me get started on this. Like I say, remove this, recap, clean up anything needs to be done. I'm going to take care of this because that's a major safety issue back here. Get that taken care of. And once I get the radio up and running in factory stock configuration, minus that it's going to have an upgraded filtering at the power line input. But as far as the receiver and the transmit is, the synthesizer, the receiver circuit, and the transmit circuit will be back to 100% bone stock. We'll do some measurements, and then we're going to try these little kits and see if there's a difference. And whichever one wins, be it factory parts, supplied kit, or like I say, I'll just use the one that most people are familiar with. Whichever one works best, I'll leave in. But yeah, it's like I say, even if there is an improvement, it's probably not going to be enough that you'd ever notice it. So I shall return. Okay, so we're getting some of this stuff taken out of this thing. I've already removed this board, so here it is. And like I say, this is why we don't like all of these wires. This yellow wire and black wire were the ones that go from this board up to the main board, and then these three wires went up to the switchboard, the speaker switch to select a crystal. But yeah, All of those, that's just variable capacitance and inductance. Just it takes the tiny, especially when it comes to capacitance, the tiniest bit of movement in a wire can have a huge change in capacitance. So yeah, you just end up with unstable frequency. So bye bye. Like I say, we will be putting the crystal back in, but this back here, this is a bit of a mess. I've got to fix this. So the input filter here, for starters, when I went to pull the wires off, yeah, they're not even really crimped that well. You can see this one just pulled out of the terminal. Yeah, that's not a very good crimp job. So yeah, I'll redo all of these, make sure they're done right. My main concern is really obvious now. The bottom side of this filter module is a can that's soldered shut, because this is like I say, a filter. It's shielded, but that's a sharp edge. Look what that has done to those two wires. That's 120 volts on those wires. Okay, as I said, power comes in here, your hot and your neutral, goes to this little filter board, and then just comes out the other side and goes up to the transformer. With this module in here, is smashing those wires. It's eventually going to cut through that, and that would have shorted out. The brown wire is your hot. That would have shorted out the hot to the chassis. Now, the chassis is grounded, but still, that's not a good idea, applying 120 volts to the chassis of your radio. Especially if your ground isn't, you don't have a good ground in your house. It might not trip the breaker. Then you've got an energized chassis. So, yeah, we'll need to take care of that. Honestly, what should have been done here is, you already had all this stuff loose. Just desolder these two wires off of this little filter board here. Pull the wires up to the top side, push out the little, well, it's not a strain relief, but the plastic grommet, and there's already another hole here. Just move that to that hole, push the wires back down through that hole, and then it'll be over here, clear. So yeah, that's what I'm going to do. The other thing is, he had this board mounted here, it kind of at an angle like that, with only one screw. There should definitely be two screws here. For starters, you see that? If there's no screw here, these capacitors are not in circuit. Yeah, so yeah, both sides of this need to be grounded to the chassis for proper grounding. So yes, again, got to take care of that. The other problem I saw with that is where this was mounted. They kind of purposefully, the original design of this, kept this board right, the original holes would have had this board over here, but it's away from this transistor a little bit more. With this being over here, you've now got 60 hertz AC coming around and then coming back out of this board right where this transistor is. This is the regulator transistor for your power supply. You're basically, the hot wire was right, let's see, put this board right back where it was, just like that. You've got 60 hertz AC. This is the hot. This is the neutral. So this is the hot line. This one has 120 volts on it. It's going to be injecting 60 hertz hum into this, because this is going to be DC on this transistor. This is after the power has gone up to the transformer, gone through the bridge rectifier to convert it into DC, then go through the power supply circuitry and filtering, but this is the regulator transistor. So this could be injecting 60 hertz AC hum straight into the regulator transistor. So not good placement. This needs to be over here somewhere, but yeah, that's not going to work like that. So yeah, I'll redo this. Yeah, always try to keep your AC separated from your DC power supply circuitry, so you're not filtering out AC hum and then unintentionally just injecting AC hum right back into your circuit. So let me get that straightened out, and then I'll start on the cap job. Well, actually rethinking this, I'm not even going to put this board back in. I had just removed the old capacitors off of here, because these are not safety rated. These are kind of early. I mean, these were what they used for safety caps back then. They were better than just using a normal, like a brown ceramic dip cap like that. But nowadays we use proper safety rated that have gone through certification. So these are X1, Y2 safety rated caps. And I was going to replace them, and then I had a light bulb go off in my head. Why am I even messing with this? All of this is inside of this. Yeah, what's... So actually, this is actually going to be a lot easier. I don't need to mess with this board and relocate it and everything. All of these parts are now inside of this EMI filter, because that's what this is. This is an EMI filter board. Yeah, all I need to do is just pull these two wires up, move this plastic bushing back here, stick the jack back in, and I'm not going to use push-on terminals. I'm going to solder the wires on. But yeah, that's it. That's all you need right there. Just put this in and attach your power line wires right there. There's no need to have a double EMI board like this. You know, that's just completely useless. You're defeating the purpose of sticking this in. You know, why would you put something like this in if you already have it? So yeah, I can put those caps back in the drawer. I don't have to use them. So yeah, that, like I say, greatly simplifies it. I don't have to worry about relocating, about having AC hum, you know, being injected in that. I'll just have the two wires come straight over to the EMI filter. And then these wires, I guess, I'm not sure why he redid these. That's not the original fuse holder, is it? Yeah, I think that's might be a replacement fuse holder. Yeah, usually what I suggest is that I'll probably redo this too. You see this? Why do we have an inch and something of wire here and, like, you know, a little 2-inch stub of wire here? Just desolder the wire. Now this is not AC, this is DC, so there's no AC on this fuse. That's after it's gone through the power supply. This is your AC-DC selector switch. But if you need to run a wire from here to here, and the wire that you have is only that long, don't just tack on an extra inch or two. Just replace the whole thing. That's... Yeah, I mean, I've worked on radios where I've seen a wire that ran from, you know, like here all the way over to here, and that wire is made up of like 4 or 5 pieces of wire all spliced together. Just put in a whole new wire. It's better, cleaner, and less problems in the future. Because if the wire is going to fail anywhere, it's usually going to fail at a splice. So just remove and replace. We'll repeal that. Okay, so I've got all of the electrolytic capacitors now replaced in the radio. I've removed the heat sinks, applied fresh heat sink compound, clean. As you can see, the boards are cleaner now. They just needed a good dusting off and vacuuming. Replaced the limiter transistor that was missing from transmit audio circuit. Let's see, what else? Took out the crystal board. I think I'd mentioned that earlier. Took out the crystal board, relocated the original crystal back down onto the main circuit board where it's supposed to be. So we got rid of all these long inductive and capacitive wires that are just going to cause nothing but frequency instability. That all needed to go anyhow because, like I say, this is going to be getting a Channel King kit in. But I wanted to put this radio back to basically stock condition. The only thing at the moment really that's not factory seconds have been enabled for the clock display, and what else? Oh, clarifier is unlocked. And speaking of the clarifier, I don't know what, now I know why the customer had a note there. Check clarifier, something's not right. Whoever did this, man, I don't know. I'm not going to say they didn't know what they were doing, because they did unlock the clarifier. But the problem was they unlocked the coarse clarifier and ended up completely disabling the fine clarifier. Now, the coarse clarifiers on these radios, when you get them unlocked, they're rather broad. So just the tiniest touch. Man, I can just imagine somebody trying to clarify somebody in with this radio using only the coarse. It'd be a little bit of a challenge. So I've fixed that now. So the fine and coarse clarifier work the way they're supposed to, but it's unlocked now. So receive and transmit frequency are locked together. That would have absolutely nothing to do with our receiver performance testing anyhow. But like I say, that is locked now. I have aligned the synthesizer circuit, and I have aligned the receiver circuit. Haven't bothered with the transmit circuit yet, because we're not testing the transmit. We're doing receiver performance testing to see if these little kits do anything. So As it is right now, it has the factory transistor and the factory diodes in it. So we're going to check SINAD, so receiver sensitivity SINAD, and what that test does is it's basically 12 dB SINAD is commonly understood to be the minimum signal needed by a receiver that it can then demodulate it, and you can have clear, readable, reception. So somebody's talking, because we're dealing with voice communications here. At a 12 dB SINAD point, that would be clear communications. And you do that by modulating your input signal, so coming in from the antenna jack, you modulate your carrier with a 1 kilohertz audio tone. And the idea is you want a minimum of 12 dB SINAD. Anything above 12 dB SINAD is better, so bigger is better when it comes to the decibel reading on a SINAD measurement. Below 12 dB SINAD, it starts to get, you'll start to get a little hard. It would be hard to copy somebody. The other two measurements we want to take are THD, which is total harmonic distortion, and THD plus noise, which is total harmonic distortion plus noise. Those measurements are taken with an input signal of 1000 microvolts. And then what you're actually measuring for there is, you want to see a lot of the tone you want to hear, that 1000 hertz tone. Now, just like when you amplify or do anything with an RF signal, you're going to have harmonics of it, which is a doubling or a tripling, and it can go in either direction. But with the total harmonic distortion measurement, we're going to do it. The communications test set, you'll see the bar graph on it. It will set the signal for the 1000 hertz audio tone that it's measuring. It'll set that as the 0 dB reference level, but then it's also going to measure the signal of the 2000 hertz audio tone, a 3000 hertz audio tone, 4000 and 5000 and on up. Those are the harmonics, because 1 times 2 is 2, 1 times 3 is 3, so the second, the third, the fourth, and the fifth harmonics. So just like I say, with RF, you end up with harmonics. Well, you want the minimum amount of harmonics. You want that signal to be as pure as possible. So, like I say, I think I got pretty much everything set up here. Already have the communications test set up. It's already hooked up. I'm actually measuring, if I turn the volume up, that right there is actually 12 dB SINAD. So we're on channel 20 in AM. Let's see here. The signal that I'm putting in is a minus 110. Let me turn actually, I can leave the volume turned up, but what I can do is, if I zoom down here to my speaker, I have it going to this external speaker, but I have a switch. There's BNC jack on the back that sends the sampled signal then out to the other communications test set. But I can turn the speaker off. So there's an internal dummy load inside of this speaker. But with a signal level of minus, and let me turn off this other radio over here. With this, and now the other thing I want to mention is, when I do an alignment on a sideband radio like this, I peak the receiver circuitry for maximum sensitivity on sideband. Now there are several of the tunable inductors, the coils and the transformers, that are shared between AM and sideband. And then there are other ones that are specific to either mode, either AM or sideband. Now, the ones that are shared between the AM and the sideband circuitry, I always peak those for maximum sensitivity in sideband. Because most people that own a sideband radio, that's what they're listening to. That's what they're talking on, is sideband. And that's the signal they're trying to squeeze out of the noise, is that little tiny guy way off in the distance. So this receiver has been peaked for maximum sensitivity on sideband. Now, when you do that, and it doesn't matter which way you do it, if you adjust it for maximum sensitivity on AM, it's going to affect your sideband receiver sensitivity usually a little bit. Same thing vice versa. If you peak it for maximum sensitivity on sideband, usually has the adverse effect of slightly decreasing sensitivity on AM. It's not a drastic change. It's measurable with instrumentation, but quite honestly, again, you get into that human hearing thing. It's barely perceptible. We're talking at such small levels that, quite honestly, it's barely perceivable. So like I say, we've got a 12 dB synad. Right now I'm measuring over on the other communications test set at minus 110. So actually, let me just pause the camera here and I'll get it swung right, because it's the other test sets I have are over on another bench over here to the left of me, so I got to swing my camera boom around, so hold on a second. Okay, so now we're over here on my other stack where I have a couple more of these. I have this one set. I'm feeding the audio signal into this one, and we're using the audio analyzer in this one. So we can see we have, actually I could turn it down, or turn the signal level down a little bit, because it's bouncing around. And that's another thing, when you're taking a synad measurement, the signal is bouncing around, because you just heard it. There's a lot of static and background noise in there. We're looking for that 12 dB synad point, so yeah, I could probably turn it down just a hair, but every once in a while it does flick down to 11 point something, so we'll just call this one, actually I need to get a piece of paper right now. We need to document our measurements. So I'm going to write down unmodified. And for 12 dB synad, we have a signal level of minus 110.0 dBm. I hate writing out, holding my hand out here. So that's our AM receiver sensitivity. Now I'm going to increase the, actually I need to write that down, AM. Now what I'm going to do is increase the signal level to 1,000 microvolts. Or if we're measuring in dBm or decibels, that would be minus 47. And now what I need to do is I'm going to adjust my volume down a little bit. It's up a little bit high. I'm going to try and keep my volume, this is the audio voltage up here, keep that approximately the same for all of our measurements. I usually take these around, turn it down, 250 millivolts usually RMS, right around there. Because we don't want to get the volume turned up too high, because if you start to get, especially if you get way high with the audio, you're going to see it, distortion just is absolutely horrible. Because now you're going to be, that's going to be the audio circuit distorting the audio signal. So right about, that looks good, 250, it's bounced around 250, 240, yeah, it's good. So now you can see what's happened to the synad measurement. The synad measurement has gone way up. And actually, let me turn the speaker back on. And you can hear there's our signal. I'll turn that back off. The synad measurement has gone way up from 12 dB, now up to 30 to 33 dB. That's because we've got a huge signal coming into the radio now. What we want to measure now, though, is the total harmonic distortion plus noise, and we can see that's bouncing right around 2.1 to 2.2%. So I'll write down THD plus noise is we'll just call that one 2.2%. And then I'm going to switch to the THD measurement. Okay, so in the THD measurement, this is the 1000 hertz audio tone. It sets that as the 0 dB reference point, and then it's measuring this. It's also measuring a 2000, 3, 4, 5, 6, 7, 8, 9 kilohertz audio tones. Those are the harmonics, the second harmonic, third, fourth, fifth, all the way out to the ninth harmonic. And we can see our THD measurement is about gets up into the 1.2s occasionally, so we'll call that one 1.2%. Okay, now what I'm going to do is I'm going to switch the radio into sideband mode. So I'm switching the radio to lower sideband. I have to change the modulation on the signal generator over here. And we're still at the same signal level. We're at 1000 microvolts or minus 47 dBm. And I'll actually turn the speaker on so you can hear it. And actually, let's go back, because just to make sure, turn the speaker back off. The audio tone's down just like 2 hertz there. I'll turn the clarifier, try and get it exactly on 1000 hertz. There we go. Yeah, 1001 hertz. That's about as close as we're going to get it with a touchy clarifier. So there we go, 1000 hertz exactly. So we have 0.9, it bounces to 1%. So I'm just going to call that at 1%. So SSB, we have THD plus noise is 1%. And if we go to THD plus noise, we have, we'll just call that one worst case, 0.9%. THD 0.9%. Okay, so swing the camera back around here. Oh shoot, forgot to take a sideband measurement in sideband as well. So let me turn the speaker on so you can hear it. I'll flip back so we can take our sideband measurement. And I'm going to start decreasing the signal generator signal level now. And now what we're looking for is that 12 dB. I got to turn the volume up because as the signal level decreases, of course, your volume's going down. And remember, I want to try and keep this somewhere probably around, right around 250 millivolts. So we have a reference level for our volume. Keep turning down. And like I say, remember, I've aligned the receiver in this radio for maximum sensitivity on sideband. Turn the volume back up a little bit. About 250. You can see we're just creeping in on 12 dB. And I'll turn it up just a hair. So I'll call this one right about there for 12 dB. It's bouncing between 12 to 13 and occasionally drops down to 11 point something. But yeah, so we'll call that one right about there. And that is at, we'll look up at the one that's sending out the signal, minus 124.6 dBm. So synad is minus 124.6 dBm. Okay, so we now have our baseline for this radio for a factory Cobra 2000 with no modifications whatsoever in the receiver circuitry. Here's what we have. In AM, we have 12 dB synad at minus 110 dBm. THD plus noise was 2.2%. THD was 1.2%. In sideband, we had a THD plus noise of 1% and THD 0.9%. So you can see sideband is going to be always going to be better than AM because the bandwidth is a lot narrower, so there's just a lot less noise getting into the receiver because it's pinched down because it's going through the crystal filter in sideband. Where in AM, the only thing it's really using is you've got the 2 filters, but this mainly, what really sets your bandwidth is a small single pole crystal filter over here and this little ceramic filter. Where in sideband, you've got this huge multi-element crystal filter that really narrows the bandwidth down so a lot less noise gets in, so we have better sensitivity measurements in sideband. And then for the 12 dB synad, we had a signal level of minus 124.6 dBm, so considerably lower than on AM. Again, that's always going to be the norm. You're going to have a lot better sensitivity measurements on sideband than you're going to have in AM. But there's our baseline with factory transistors, factory diodes. Now, one thing I think I forgot to mention before, when I mentioned about doing this, was I didn't go over the diodes and the transistors really in detail, and I probably should. And it's the reason I do not modify these. I'm not going to lie to you, just like probably every other person that works on CBs, I started out, I used to do these modifications. This right here, well, maybe not these diodes and that transistor. I did the normal 2SC2999 and the 1N6263 Schottky diode modifications. And I learned over time, just from experience, installing them, testing radios before and after, it really didn't make a difference. The transistor really doesn't make a difference. Now, it's called the first RF amplifier. Quite honestly, it doesn't do that much amplifying. That's because it's in a common base configuration. So if we take a look at the schematic, here's our first RF amp, here's our second RF amp. So the signal comes in, is fed in from the antenna, comes up here. Here's our front end protection diodes right here, comes through transformer L4, which does a little bit of shaping, and then we have, this is the transistor that most people would replace. And the modification, actually I need to look in my book here. I think it should take, like, it's honestly been years since I did one of those. Let's see. Remove TR14 and install your new transistor, and then you remove TR19 and then install the transistor that was removed from TR14's position in TR19's position. So let me, actually I need to find TR19 here on the schematic. 16, should be right over, I'm used to looking at a SAM schematic, and this is a factory one, so the layout's a little bit different here. What the hell was 19? 18, oh there it is, bottom transformer, double transformer, yeah, TR19. Okay, so the modification most people do is they pull this transistor out, they install a 2SC2999, and they move it, and then they remove this transistor, TR19, and they install that original transistor in that transistor's place. Now, this transistor, as you can see, has the base tied down here. The signal's actually coming in right here and coming out and going. So these two transistors are mainly used for impedance matching. There is a little bit of amplification there, but most of your gain is not attained here. It's attained later stages in the receiver circuitry. So for those people to say, you stick in the transistor with the better gain here, you're going to get, it's going to boost your signal. Not really. It boosts, and that's the problem. This is right at the front end. The next thing back from here, if you follow it down, it goes to the antenna connector. This transistor, any amplification that it does, it's amplifying everything that's coming into the radio. It has not gone through any IF mixer stages to convert it down to a much narrower band signal. Now this one, as you can see, is connected differently. This one actually has the input going into the base, so this one has a lot higher gain. So you're going to get some gain here. So yeah, it's like I say, the juice you may get a little bit of better gain, but a lot of times what you end up with is you amplify the signal you want, but you also amplify the noise. I can get the same result by doing that, turning the volume up a little bit higher. That's the effect of turning the volume control up. You're amplifying everything. That's the same thing you're doing by replacing that transistor. It's amplifying everything, noise and signal that you want. The other problem, and I think it's even, I don't want to say severe, but replacing the diodes. This is the diode right here, the 1N6060Ps, are what are factory in here. They're a germanium diode. They're the larger glass diodes that you see in these radios. Clear glass tube with a little black line on them. It just looks like it looks in the picture there, but they're bigger than the silicon diodes in here. The The problem is when you remove a germanium diode and install a Schottky diode, the Schottky diode has a lower forward voltage, okay? It's VF. That's the voltage that the diode turns on. A diode basically is a one-way switch. It only allows current through in one direction and blocks it in the other direction. But it also is off until the forward voltage gets up high enough that the diode can actually turn on. Because remember, it's a semiconductor, so it needs some voltage. It needs a certain level of voltage there, potential, to turn it on. This diode has a lot higher voltage than either the 1N6263, which is what most people use, or the diodes that are included in this little kit. They are BAT85. So I pulled the data sheet up for all three of these, so we can actually compare that forward voltage. Now, unfortunately, data sheets, and you can see all three of these diodes made by three different manufacturers. You know, this one's from NXP, this one's from ST, and this one's from Tiatron. So they all have a different reference current that they're using, the forward current, but luckily all of these data sheets also have the graphs, so we can come up with the same specification at the same current level that they're using for this 1N60 here. So if we take a look at this one, we can see the test conditions are 25 degrees Celsius. V forward, the maximum instantaneous forward voltage, is 1 volt at 5 milliamps forward current. Okay. What is that noise I'm hearing? Oh, that's another radio I got. I got monitor radios on all over the place here. But it's 1 volt with a forward current of 5 milliamps. Now if we go to the next one, this is the 1N6263, which is the diode most people are familiar with, the little blue diodes that you see. Okay, we can see here we have VF. Now this one is done, here's our 25 degrees Celsius, so same temperature conditions. The problem is, now they do give it two different currents, but they do it at 1 milliamp and at 15 milliamps. This one was done with a forward current of 5 milliamps. So luckily, they have the graph on the back here. So if you go up to the 5 milliamp, now this is logarithmic here, but we have our 5 milliamp line. We're going to look for this 25 degrees Celsius arc. That's the center one here. So you follow that up to where it crosses over to 5 milliamps, follow down. So you're looking at, and I actually wrote that here on the front, you're looking at about 0.45 volts forward voltage at 5 milliamps. This one's 1 volt. This one's a little bit less than a half a volt, so it has half the turn-on voltage as that germanium diode does. If we look at the BAT85, V forward at 25 degrees Celsius, now again they take it at IF at 10 milliamps, is 400 millivolts, and that's actually on the second page of this data sheet. So if we go up to the 5 milliamp line, our 25 degrees Celsius is line number 3, so that's the far right hand line. If you follow that up and then come down, and I again wrote that on the front, that's actually the front is the next page here, is approximately 0.275 volts of forward voltage at 5 milliamps. So it's close to half of what this one is. Not quite, but it's, so you're looking at 1 volt from the factory. What most people do is 0.45 volt turn-on voltage for this Schottky diode, and then the ones that are included in the kit that was sent here, it's approximately 0.275 volts forward voltage. Now, what's all that mean? Who cares about that turn-on voltage? Well, that's why they put them in. They say, well, with the lower turn-on voltage, you'll get, the signal can get through easier because it doesn't take as much voltage to turn on that diode. Yeah, maybe, but it causes a horrible problem. And if you own a certain vintage of Ranger Galaxy radios, or honestly radios that were made by any of those companies, the problem you're probably familiar with in a lot of those radios is crashing or popping noise in your receiver. When somebody's transmitting with a strong signal and they unkey, you'll get this pop or this really loud crack in your speakers. You know what's causing that? Schottky diodes. There for a while they were putting in Schottky diodes in those radios. Now there is a way around it, and I think some of the later Galaxy Rangers that I've seen, they've actually fixed that. They've added basically a bias circuit to that to basically tickle the little diodes. So they're supplying it with a tiny amount of voltage, so it never completely shuts off the whole way. But that's the problem with those diodes. You get that crash noise, and you end up with a pop or a really loud crack in your speaker audio, and it drives people nuts. I've had radios like this that had Schottky diodes installed, and they sent the radio to me asking if I can get rid of that horrible popping or cracking noise out of their speaker. And they're like, what can you do about it? I don't know what's wrong with the radio. Well, it's not so much that there's something wrong with the radio, other than somebody did one of these modifications. They put these diodes in, and that causes that damn noise because the turn-on voltage is so low. You need a diode. They picked these diodes that they put in these radios for a specific reason. The engineers knew what turn-on voltage they wanted. Schottky diodes were around when these radios were made. They could have very easily, if they wanted a Schottky diode, they could have installed a Schottky diode in these radios. They used germanium diodes for a specific reason. They have a higher turn-on voltage. They didn't use silicon diodes because silicon diodes have an even higher turn-on voltage than germanium diodes do. So, yeah, that's why I always say, honestly, most of the time, you don't need to modify this stuff. Just let it the way the factory, the way the engineers, now granted this is a Cobra, but it was made by Uniden. Leave it the way Uniden engineers designed it to work. They're engineers. They knew what they were doing when they looked over data sheets back in the day. So, but we're going to try it. So now I'm going to turn the radio off here. I will install this kit first. So this is the one that was supplied by the customer. We'll stick these in, see what it sounds like. I'm not going to describe all the measurements. Next time you see the communications test set, I'm just going to run through it. I'm not going to describe. I mean, I'll tell you the measurement that I'm taking, but I'm not going to describe in detail what SINAD, THD, and THD plus noise is. But get these installed. We'll take measurements with this one. The exact, same measurements that we just took here with these, and then I'll install the 2SC2999 and the 1N6263 Schottky diodes, which is what most people are familiar with. And we'll see, is there a difference, and is the juice worth the squeezing? Like I say, I do think we will have an improvement, but quite honestly, it's going to be so low, it's such a low number, it's really not going to be perceptible by the human ear. More importantly, the diodes especially cause problems when you get that receiver crashing sound, when a strong signal, somebody unkeys, and that's a artifact of the AGC circuit, its reaction time, the diode, how fast it turns on and off, and it's forward voltage. There's a whole lot of things in this receiver that all play in together, and just throwing in one new part in there, you haven't modified the rest of the circuit to work with that new diode. So let me get those parts installed and we'll take some more measurements. Okay, so we're ready to move on with testing with the little kit that the customer sent, which has the BAT85 Schottky diodes and the 2SC, what the hell is it, 1730 transistor. Took that transistor out, replaced it with the supplied transistor, then took that transistor and moved it over to TR19's position, thereby removing this 2SC945 and installing the transistor that was here over here. That's, like I say, that's the normal modification on these radios when they do the 5-piece kit. And then here are the 4 germanium diodes that were removed out of the radio. So you can see we now have, instead of the germanium diodes, find it here in the camera view, we now have the smaller little BAT85 diodes there, and then that diode there, and right there were replaced. And like I say, this transistor, if I get the camera so you can actually see the part number on it, see, that's now a 2SC, whatever I said, 1730, and then the transistor that was in this location was removed and moved over to this location. And that transistor that was removed there is this one. That's the one that was replaced. So let's do the test again. Now, one thing I did change was my paper. The Post-it note, I was going to quickly run out of room here, so I just took these measurements so you can see they're still the same. I wrote these measurements down on here. So I've made 3 columns basically. This is the test that we just performed here, so I'll just leave this sitting here so you can compare if you want to make sure I wrote the same thing down. So our 12 dB sinad on AM unmodified was minus 110 dBm. THD, now I'm not going to write down these voltage levels because these are just going to stay the same for all the measurements. The input signal level for THD and THD plus noise, but that's at 1000 microvolts or minus 47 dBm. So that's 1000 microvolts into 50 ohms or minus 47 dBm. So our THD was 1.2%. See, 1.2%. THD plus noise was 2.2, 2.2. And then in sideband we had a 12 dB sinad with an input signal of minus 124.6, minus 124.6. Our THD was 0.9%, 0.9%, and THD plus noise was 1% and 1%. Now, one thing really quick to notice, the THD plus noise measurement is always going to be worse than your THD measurement. The reason is this measurement here is only measuring the harmonics. So 1.2% of the signal or the audio that's coming out of the speaker or the speaker jack on this radio is harmonic energy. And when we measured it here. But when we took the THD plus noise measurement, 2.2%. So it went up by one full percent. The reason for that is that's because it's also measuring the noise. So that's the 1.2% of harmonic distortion, plus there's also an additional 1% of just noise. So that's why that measurement's always going to be higher than just the THD alone. So let's now repeat the same measurements. So I've got the communications test set up here already set up. We're still in sideband mode, the radio's still in sideband. And then if we come down to this one down here, the camera down a little bit, and I'm just going to leave the camera on this communications test set. I'll turn the volume up, set it to 250 millivolt RMS. Right about there. And you can see we're bouncing. Let me just turn the signal level up. Make sure we have our 1 kilohertz tone there. Yep, it's just jiggling back and forth a few tenths of a hertz. So that's right at 1 kilohertz. And now what we're looking for is 12 dB sinad. I'm going to reduce the input signal level. Right about there. Up a little bit. Yeah, it's bouncing between 12 to 13. You saw it drop down to 11, so right about there. So we'll call that our 12 dB point, and that is at minus 100, and just so you can see it, it's less, or a higher signal level, not less, it's a higher signal. Minus 122.4 dBm. We were getting 12 dB sinad at minus 124.6 before. That's a higher signal level, minus 122. So our receiver sensitivity on sideband has gotten worse. So let me write that down. Let's see, sideband. Actually, what I want to do, let me pause the camera because I didn't plan ahead. Let me turn the volume down. I should have written out 12 dB sinad, THD, and THD plus noise in all these columns. So let me pause the camera and write down that text down here. Okay, turn the volume back down there. So now you can see I've just transposed the words down here, so I don't have to do that on camera. So I've filled in our 12 dB sinad is at minus 122.4 dBm, a stronger signal than it was from the factory. So our receive sensitivity has gotten worse. It requires more signal input to get 12 dB synad in sideband. So let me get back over here now, and come on, camera, down here, you're leveled out. Okay, turn the volume up so you can hear it there. Now what we're going to measure is the THD and the THD plus noise, and if you remember, that's done at 1,000 microvolts or minus 47 dBm signal level input. So let me increase that to minus 47 dBm. You see our audio voltage shot up because it's a huge signal now. Turn that back down to about 250 millivolts. Okay. Looks like I might have bumped the clarifier. So I'm turning the clarifier to make sure we have our 1000 hertz tone. Because remember, as you turn the clarifier on sideband, if you can hear that, your audio frequency is going to change. Right about there. We've got 1001 hertz. Can I get it down anymore? Oh, clarifiers are so touchy. 998. There we go, 999.8 to 1. Okay. And we have a THD plus noise of, we'll call that one 2.2%. Let me write that down. 2.2%. And our THD is, we'll call that one 2.1. Just like I did on the last one, I'm going with whatever the highest reading I see there. So we'll call that one right around, 2.1. It bounces up to 2.1%. Okay, let me turn the volume down there. Now we'll go back to this screen. I'll switch the signal generator into AM modulation now. Switch the radio to AM. And I'm going to go for 250 millivolts audio. Okay, right about 250 volts of audio. And we're now in AM mode with the same signal level, minus 47 dBm or 1,000 microvolts. We have a THD plus noise of, I see it bouncing up to 3, so we'll call that 3%. And our THD measurement is bouncing around a little bit. I see 0.8% occasionally, but I'm going to call that 0.7. Seems to hang around 0.7 a little bit more. So we'll call it THD of 0.7%. And let me turn the volume down. And let's have a look at the measurements. So our in AM we had 1.2% THD. That actually improved. That got better. AM THD, or total harmonic distortion. It was 1.2%, it's now 0.7%. THD plus noise was 2.2%. That got worse. So that means there's more noise. Again, this is a lot of times the problem with these modifications. You put in diodes that have lower turn-on voltages, it takes less, pardon my French, crap to turn them on. They turn on and let more of that crap in to get demodulated, and you end up hearing it. So, yeah, the harmonic distortion for some strange reason went down, but the harmonic distortion plus noise actually increased. And on sideband, we had 0.9% THD. That actually shot up in sideband. That went up to 2.1%. and THD plus noise was 1%. That went up to 2.2%. So the oh, we didn't measure SINAD, did we? No, we didn't. Sorry about that. Forgot one measurement. Or did we do that and I forgot to write it down? No, actually we didn't do it yet. So let me reduce the signal. No, not the frequency. RF level, we'll just start off at -110. Turn the volume up. Approximately 250 millivolts of audio. Okay, and I need to increase the signal level. Turn the volume down a little bit, get our 250 millivolts. I'm going to call it right about there. I see 11, 12. Occasionally it would bounce, it would bump up about 0.1 dBm. Yeah, there was a 13, so it drops occasionally, drops to 11, but it's staying right around in the 12 region there. So we'll call that one for our 12 dB SINAD point, and that is -106 dBm. And if we look down at our paper, I just say -106.5. And let me turn that annoying volume down. AM sensitivity also decreased. Sideband sensitivity decreased. AM sensitivity decreased. THD and THD plus noise got worse in sideband. THD plus noise definitely got worse in AM. And for some strange reason, THD got better. Got a little bit of improvement in THD, but that's being overwhelmed by the noise that's getting into the receiver now. So, bad 85 diodes and 2SC1730, in my opinion, absolute waste of time and money. You had to buy the parts and you have to pay somebody to stick them in. You're actually decreasing the performance of your radio. Waste of money. Save your money, people. And remember, those Schottky diodes cause popping or crackling noise, whatever you want to call it. When you have a signal coming in, somebody unkeys their mic, the signal disappears, you'll get that popping noise because of the time that it takes for the AGC to react to that and the turn-off time for the diodes. So, because they have such a low turn-on voltage. So, yeah, it's basically the net effect is worse performance. So, let me turn the radio off again, unhook it from the power supply, and we shall get some of the 1N6263 diodes installed and a 2SC2999. So this time I don't need to move that one transistor over here. That one's already over here. I just need to take the 1730 out, put in a 2999, and again replace those two diodes and the two diodes up here. And I'll be back and we'll take our last set of measurements. Okay, so ready for the last test now. We're testing with the 1N6263 Schottky diodes and a 2SC2999 transistor for the first RF amp. So that transistor, and you can see that's the little small guy because they're a different package size, the 2999s. And you can see we have the two 1N6263 Schottky diodes there, and right down here you can see there's the two little blue diodes. And yes, these components, the ones that I installed, now I have no idea the validity of original manufacture on those parts that the customer sent. I don't know. I'm not sure where he bought that little kit, possibly off eBay. I'm not going to assume. I don't know because I didn't buy that kit. But the transistor and those diodes, I guarantee are original manufacturer because I bought those from DigiKey. I've got an entire reel of those diodes. Those are, in fact, I keep some in the drawer over here, cut off of the strip. Let me grab one. Those are, if we can get it to focus, I gotta find it on the diode first. Oh, where is it? There's the logo right there. There's a little ST semiconductor logo. I don't know how it shows up in the camera or not. But yes, these are the real deals. Same thing with the transistor. Years ago I got a reel of those as well. Off of DigiKey, because like I say, years ago I used to do these modifications and then I stopped. So let's do a test now and see how this performs. So where are we at? We have the radios in AM. Signal generator's still set up actually just like it was before, where we left off, because there's our 106, yeah, minus 106.5 dBm, which was the 12 dB synad point for the last set of diodes and transistor. So let's go down here. The camera down. Okay, turn the volume up. Get our 250 millivolts of audio. And, well, they work better. No, I'm not saying better than the factory. But you can see we now have well over, we're bouncing off 14 dBm. So, yeah, that's better than those ones the customer sent. So let's turn the signal level down until we get to the 12 dB point. Won't have to go too far here. A little bit too far. Bouncing between 12, 13, I'll drop down 0.1 more dBm. Looks like a good, pretty steady 12 dB synad right there. And we are at minus 109 dBm. That, zoomed in too far. We had minus 110 before, had a minus 106, so it's worse than factory, but better than these. Because minus 110 is lower than minus 109. You gotta remember, you're in the negatives, you're counting backwards. So yeah, it requires a little bit, not much. That's really close. And honestly, you'd probably never notice that 1 dBm of signal intensity. You'd never notice that sensitivity. But it is definitely better than these diodes and transistor. So let's now increase the signal level up to minus 47 dBm. Adjust the volume for 250 millivolts, right about there. And we have just let her see what the highest gets to. We'll call that at 2.5%. Let's see, THD plus noise, 2.5%. Oh, and I forgot to write down minus 109 dBm for our synad measurement. So now let's measure THD. It's getting up to 0.9. I'm seeing it bouncing there pretty regularly. Maybe 0.8. I'll call that one at 0.8% THD. And now let me get set up for sideband. Switch the radio into sideband. And let's go back here. Get our audio level set to 250 millivolts. And we're almost, let me see if I can just touch up the clarifier. There we go, 1001. There we go, even better. 1000, yeah, we're right at 1001 hertz. Turn the volume down. Oh, actually it's already at 250 millivolts, isn't it? Okay. And we have a THD plus noise, we'll call that one, gets up to 2.2, so we'll call that one at 2.2%. 2.2%. And THD, I'm seeing 1.9, even as high as 2. And it's bouncing up to 2 pretty regularly. So I'll call that one at 2% THD. And now we'll go back here and we'll decrease the signal level till we get to our 12 dB points. I'll just start off at minus 120 dBm. Turn the volume up, get our 250 millivolts. And the signal down. Turn the volume up. Okay, so we're right at around 250 millivolts audio. Turn the signal down a little more. Okay, there it's bouncing between 11 to 13, so it's staying right in the 12 dB synad range right there. And that is at minus 123.8. So minus 123.8. Okay, so test complete. So how did that make out? Minus 109, worse than factory, better than the BAT85 2SC 1730s. 0.8%, 0.7%, 1.2% THD. THD in AM was best with the BAT85 and the 1730 transistor. Very, very close with the 1N6263s and the 2SC 2999. More importantly, though, is THD plus noise. You can see we had 2.2% when we measure THD with the noise figure, so 2.2%, 3%, and 2.5%. So THD plus noise was best bone stock unmodified. In sideband for 12 dB synad, we had minus 124.6. With the customer supplied parts, we had minus 122.4. That's a larger signal than that. And with the 299 and the 6263s, we had 123.8, which is better than the customer supplied parts, but a little bit worse than unmodified. So again, unmodified came out best. THD was at 2%. 2.1 and 0.9%. THD was best unmodified, and THD plus noise was 2.2%. Again, 2.2% and 1%. So when you account for the measure of THD plus noise, again, best unmodified. The only improvement we had here was what? THD in AM. That's it. Well, actually, THD even in sideband was better by 0.2% here. So we had slightly, or no, wait a minute, 2.2. Yeah, 2.2, 2.2. Oh no, that's sideband down here. I'm comparing sideband to AM. AM was what? 2.5, 3, and 2.2. Yeah, so actually it was just THD. That's the only thing that was better. We had 1.2% THD unmodified, 0.7 with the customer supplied parts, 0.8% with the 1N6263 2SC 2999. So yeah, it's pretty clear right here from the measurements. Unmodified came out best. And remember, unmodified is not going to have that blasted popping or cracking noise when somebody unkeys a microphone and the signal crashes. And so yeah, there you go. As you always hear me say, leave your radio factory. If you want to do something to your radio and to improve it, it's old, replace the electrolytic capacitors, do a transceiver alignment. That's all you need to do. The engineers actually knew what they were doing when they made these radios. Leave it alone, folks. So let me finish up the work I got to do. I have to align the transmitter circuitry now, and I do need to rewire the speaker switch. That's just completely unhooked right now, because that was part of the channel modification. The speaker 1 and speaker 2 jacks are just on all the time, so I need to reconnect that switch, and then I can put the Channel King board in it. So there you go. Save your money. Don't do the receive modification, because you'll receive less. Okay, so I actually got done this test, gave Mark a quick call and said, surprise, surprise, guess what? Just what I was expecting, either no improvement or possibly degradation. And honestly, these levels, these changes you're seeing here, with maybe the exception of the THD plus noises, man, that's, I don't know, even those, yeah, in sideband, an increase from 1 to 2.2% might be perceptible. If you've got a good ear, and trust me, honestly, most people that think they have the golden ear really don't, unless you've run sound for a long time, or you are a dedicated radio listener. I mean, that's all you do all day is listen to radios, kind of like I do, because I work on them all the time. You may not even perceive like this 1.2% higher THD plus noise than here, but Mark brought up a point. Now, Mark, he does YouTube videos. He's the guy that makes the Channel King boards, okay? He's an electrical engineer. He has debunked the transistor mod, the 2SC2999 modification before, but now, he'd never tried this transistor here, this 2SC1730 and the BAT85 diodes. But he said, now I don't get online and read forums and crap. All I do is work on it. I don't have time for that. But he said he has read where some people say that doing the diodes only, they're saying that's better, okay? Leave the transistors alone, only change the diodes. So I figured, what the heck? The radio's here. Still got all the parts out here. We'll try that. But we're not going to try just the diodes. So I've added 2 columns here. I've added a column for diodes only, and I've added a column for transistor only. So I'm going to now remove put the transistors back the way they were from the factory. We don't need to test this because we know what the factory is. But in this case, we're going to put the BAT85 diodes in with factory transistors, and we'll see what the difference is. We'll do the same thing here. We'll put in the 1N6263 diodes, factory, leave the factory transistor in, and see what the improvement is. Then I'll put the factory 1N60 diodes back into the radio, and we'll try it and see what the difference is with just the 2SC1730 transistor. And then we'll try it again with a 2SC2999 transistor. So that'll give us even some more, because I know what's going to happen, and I'll post this video, and people are going to say, yeah, but I use only the diodes, and it sounds better. Honestly, people, these readings right here, it's like I say, minus 124.6, minus 122.4, minus 123.8 dBm. You're not going to notice that. That's why I say the juice ain't worth the squeezing. Minus 109, minus 106.5, minus 110, you'd probably never notice the difference quite. You may think you have some superb jackrabbit hearing, but you don't. You probably never notice any of these. But we'll just do that, just to, squash any argument before it comes up. We'll try just the diodes, we'll try just the transistors, see if there's a change. And if you have any idea, now remember, it's the customer's radio. When I get done with this, it's getting boxed up and sent back to the customer. But in the future, if anybody has any other suggestions for different diodes or maybe different transistors, the next time I get one of these chassis on the bench, could be a Uniden, could be anybody that used the Uniden chassis like this. I've always got these chassis here, coming in across the bench. So maybe in the future, if somebody wants me to try a different combination of parts and take some quantitative measurements, compare them from factory to modified, I'll be happy to perform the test again with different parts to see if there's a difference. If somebody wants to supply the parts, hey, that's fine, but don't expect to send the parts in and I'm going to shoot the video the next day. You know, it could be months until I get around to it, but, you know, whenever I have time, and a radio that I'm actually working on to try them on. I'm not going to go pulling one of my radios to test them, because all of my radios are bone stock factory. Because, like I say, the proof's in the pudding. Usually the factory receiver's better than it is when it's modified. But yeah, like I say, we'll test this, and then if you have any suggestions for other diodes or transistors, honestly, when it comes to the Schottky diodes, I think we can see... and we'll actually, now I'll shut my mouth there. I'm not going to say better or worse. We need to try them by themselves first. Same thing with the transistors. We need to try them by themselves first. Then I'll be able to make a little bit of a better argument of which of these components is causing this worse distortion and receiver sensitivity. Is it the transistor, or is it the diodes, or is it both? I may replace only one or the other, and it'll get a little bit better, And then same thing with the transistor. If you use only the transistor, it may get a little bit better, I'm thinking the receive sensitivity, most of this is probably due to the transistor swap. I don't think the Schottky diodes have that much of a change here. Could be wrong, because they do have a lower forward voltage, but yeah, we'll see. Like I say, we'll try them, and we'll see what the results are. So let me swap out the diodes. Actually, I don't need to swap out the diodes. The blue good God, I'll get it. 1N6263s are already in here, so I'll leave them in here. I'll take this transistor out, the 2999. I'll take that transistor out, put it back over here where it was, and then put the factory 2SC945 back over here in TR19's position. We'll run the test with these Schottky diodes, then I'll swap them out for those bad 85s. Then I'll put the 1N60 diodes back in here, and then we'll swap the transistors again, and we'll try it with just the transistors replaced with factory diodes. And so we'll get, 4 more video segments here. 2 different diode videos and video clips. Two different diode video clips and 2 different transistor video clips. And then we can compare again all the results. Okay, so this is with factory transistors installed and 1N6263 Schottky diodes only installed. I am in sideband, which is where the last test we took, so that's where everything's already set up for. I'll turn the volume up. Get our 250 millivolts approximately of audio voltage. And it looks like our synad went up. So we're at minus 123.8 dBm, which is where we left off with the last test. So it looks like I can decrease the signal level. So the transistors obviously make make the sensitivity worse. A little too far. 11, 12, yep, bouncing right in the middle there, so it's hanging right on 12 right there. So I'll call that one at minus 124.9. Write that down. Let's see, making sure I get this in the right column. Diodes only, and that is the 6263 diodes. So minus 124.9. We'll now do our THD and THD plus noise measurements. So let me turn the volume down so we don't get blown out of our chairs. Increase the signal level to minus 47 dBm, or 1000 microvolts into 50 ohms. Turn our volume. Get our 250 millivolts audio voltage. And looks like the clarifier got bumped there when I moved my arm. Come on. A little bit too far. Right there. 1000 hertz. Okay. So we have a THD plus noise of, we'll call that one 0.9%. Whew, huge difference there. Obviously transistors, 0.9%. And THD, and we're getting up to 0.8, so we'll call that one at 0.8%. Okay, now we'll switch into AM. Okay. We're in AM. We're already at minus 47 dBm, so we'll do the same thing. We check our audio level now. I need to turn it up. Sideband's always louder. So there's our 250 millivolts, and we're at, we'll call that at 2. I'm seeing it get up to 2.4%. So 2.4% THD plus noise. And THD, I'm seeing that get up to 1.2, so we'll call that one at 1.2%. And now we'll switch back and decrease the signal level. We'll start off at minus 110. No, not 1,000. Minus 110. Turn the volume up. Get our 250. Looks like we're almost already right there. Around 110 is really close. Turn it up a little. Like I say, what I'm looking for is where it stays mainly rated 12, occasionally might bounce to the high 11s or really low 13s. There, we've got 13, 11, 12, so right there. And we're at minus 109.5 dBm. Minus 109.5 dBm. I'll turn the volume down, I'll turn the camera off. I'm going to now remove the 1N6263 diodes and install the BAT85 diodes, and we'll repeat the test again. Okay, so I've taken out the 1N6263 diodes, installed the BAT85 diodes, and this is with factory transistor installed. So I'll turn the volume up, and we'll start where we left off, which was the sinad measurement in AM. Get up to 250 millivolts audio here. Okay, and I'm not expecting really to see any change between the two different shot keys, but yeah, looks like it's exactly the same. We're right there at 12 dB and we're still at minus 109.5 dBm. 9.5. So that apparently had absolutely no difference between the two diodes on sensitivity. We increased the signal level to minus 47 dBm. And turn the volume up till we get to 250. Okay. And we have I'm seeing as high as 2.4% THD plus noise. 2.4%. And THD, we're getting, call that one as high as what, 1.1? Yeah, we'll call that one at 1.1%. Okay, turn the volume down, switch into lower sideband, and back to this one. Our audio frequency is still perfect. Turn the volume, get our 250, right there. And let's let's see, we have a THD plus noise of, we'll call that one at 0.9%. 0.9%. THD, we'll call that one at 0.8%. And now we'll go for synad. So I'll decrease the signal level. Start off at minus 120. Volume up a little bit more. Bring it up just a hair. Okay. Looks like that's pretty good, bouncing, staying mainly in 12 and occasionally 11 to 13. So, and that's at minus 124.9 dBm. Minus 124.9 dBm. Okay, so now I will put the factory 1N60 diodes in and we'll try the different transistors. Okay, so we're now with factory 1N60 diodes, excuse me. And what transistor is that? That is the 2SC1730 first RF amp installed, and the transistor out of its place moved over to the TR19 position. So let's see, where were we? In sideband last. Turn the volume up here. And it looks like our receiver performance dropped drastically. So it is the transistors definitely causing the reduction in sensitivity. So let me turn the signal level up. Turn the volume down. I'm on 250, there we go, about 250 there. Turn the signal up. And turn the volume down a little bit, get our 250 millivolts. About there, and going 11 to 12, 11, 12, I'm seeing 13, so we're hovering right there at 12 dB, and we are at minus 122.5 dBm. Synad, so minus 122.5 dBm. Turn the volume down. I'll increase the signal level to minus 47 dBm. Right about there's 250 millivolts. And we have a THD plus noise. We'll call that one at 2.2%. Let's see, where am I at on my chart here? THD plus noise, sideband, 2.2%. And THD, I'm seeing up high is about 1.8%. I even saw 2 flash up there. Yeah, I think we'll call that one at 2%. 2.0%. Okay, turn the volume down. Switch to AM now. And turn the volume back up. And get our 250 millivolts. And we have, call that one, it's flashing up to high as 3% THD plus noise. I think we'll call that one at 3%. And THD. And it's getting up to 1%. Yeah, I'll call that one at 1%. And now we'll check Synad. We'll start off at minus 110. Volume up here. Increase my signal level. Volume down a little. 250 millivolts of audio. Turn the signal down a hair. And I'd call that one right about there. I'm seeing 11 to 13, so it's staying mainly at 12. So that is at minus 107.7. Minus 107.7. Okay, so I will now remove the 2SC1730 and install the 2SC2999, and we'll repeat the test for the last segment. Okay, so this is factory diodes with a 2SC2999 transistor. And we'll start where we left off with the last test, which is in AM, doing a Synad measurement. Turn it up till we get to 250 millivolts audio, about there, and it looks like receive sensitivity may actually have improved slightly, because I'm not seeing it bounce down. It's staying up in the 13 range, so it looks like the 2999's got a little bit better than that 1730. I'm reducing the signal level here. Volume up a hair. Okay, now it's down to 11 now. Go up a little. I gotta turn my volume up too. Okay. Yeah, it's bounced between 11 to 13, so staying at 12 dB mainly, 250, and we are at minus 109 dBm. Minus 109 dBm. Okay, turn the volume down. I'll increase the signal level to minus 47 dBm. Turn up for 250 millivolts of audio voltage. And we have a THD plus noise. I'm seeing it get up to as much as 2.6%. So I'll call that one at 2.6% THD plus noise. And THD. Call that one as high as, let's say, 0.8 is about as high as I'm seeing that go. Yeah, we'll call that at 0.8%. Okay, now we'll switch to sideband. Back to the analyzer. Turn the volume up for 250 millivolts audio voltage. And we have THD plus noise. I'll call that one at 2.2%. And THD, I'd call that one at maximum, what, 2%. And now we'll check synad. So reduce our signal level down. We'll start out at minus 120. Turn the volume up. Reduce the signal level. Volume up a little more. Okay. Let's see, 11, 12. Okay, and bouncing up to 13 occasionally. So staying mainly at 12. And that is minus 123.7 dBm. Okay, let me get the radio off the bench here. I'm going to take a highlighter and highlight the best result between the combination of parts, and we'll see what she looks like. Okay, so there may be a little bit of truth to the people that are saying the Schottky diodes do net some better results, it looks like. Our best AM receive sensitivity was a bone stock radio, as was our best THD plus noise in AM, had the best result. The best THD only in AM was with the BAT85 and 2SC 1730 transistor and diode combination. Let's see, now honestly, like I said, I wouldn't worry so much about THD. I'm always more concerned about the THD plus noise, because that's also measuring the noise component, and you can see there's a lot of noise there. There's more noise than there is up here. So in AM, I'm going to say a bone stock radio is best. Kind of interesting, in sideband, it looks like the diodes have the highest. Now, not by much. We can see we had a bone stock radio minus 124.6 dBm for 12 dB synad. And you'll notice I've got 3 orange dots here and 3 orange dots here, because the results were exactly the same. Minus 124.9, 0.8%, 0.9%. Those were exactly the same for sideband with either diode and, with the factory transistor. And we can also see what the transistor does for us. Notice there's no orange dots over here. So the transistor is obviously the one that is reducing our performance. That's the one that's causing the most distortion, and the lowest sensitivity are the transistor modifications. So I would not definitely do not do the transistor modifications. Now, this difference we're seeing here, honestly, if you look at that, minus 124.9 for both the Schottky diodes, and what do we have, minus 124.6 dBm up here, I'd call that even, quite honestly. That, to me, would be within the margin of error. If you consider there's going to be variables, you have to adjust the volume to get to 250 millivolts. Clarifier, I'd get it exactly at 1 kilohertz. It's a analog control potentiometer. I'd call this within the margin of error. Quite honestly, I'd say, and I mean, you can see the difference. 0.3 dBm of difference. You will never, trust me, there is not a single person on the face of this planet, I don't care how good your hearing is, I don't care if you've worked in a professional sound studio since the time you were born, no one can hear a 0.3 dBm receiver sensitivity difference. That's just, there's no way. If it was several dBm, whole numbers, but about 0.3 dBm, this pretty much shows that there may be a tiny bit of improvement if you only do the diodes, but like I say, that's within the margin of error, only 0.3 dBm difference. And by replacing the Schottky diode, you've upped your likelihood of getting that annoying pop or crack noise when you have signal dropout, when somebody stops transmitting. So, yeah, stick with a bone stock radio. It doesn't get much better than this, folks. So that's my conclusion. Stick with an unmodified radio. It's hard to improve on perfection, quite honestly. Uniden had a really good chassis there, and yeah, trying to tinker around with receiver component parts, it ain't doing nothing really. Like I say, that's margin of error there. So yeah, stick with the factory stuff. So let me get the rest of the radio done. I'll get her back up and then see if there's any skip on. There was a little bit of skip on earlier, but probably by the time I get everything done, it's going to be nighttime, and I doubt there'll be anything to listen to. But we'll turn the radio on and see if there is. Okay, so I got her all completed now. The only other thing I really had to do was the guy said, go do your voting. Actually, speaking of which, I just took that out of my shirt pocket. There's my proof that I went and voted today. The tear tag off my ballot. Very important. Anyhow, only other things I had to do to this was install the Channel King board, which has been done. Reconnected the speaker switch, because it would help if I turned the squelch down. So, speaker switch works now. And then did the full alignment on it. Now, I've actually redone the receiver alignment on this from previously when we did the testing. For starters, this has been put back to a factory stock receiver. As I showed in the test, trying to do those receiver modifications, you might get a little bit of gain here in one spot, but you end up with higher total harmonic distortion, and the important point is plus noise. THD might drop, but the noise increases. And a big problem there is transistors. If you use transistors that have higher gain, you have to remember the gain, depending on the gain of the transistor, can affect the bandwidth, and affecting the bandwidth affects how much noise gets into the radio. Greater bandwidth, more noise. Kind of reflected in that THD plus noise measurement that the noise goes up. So, any tiny gain that you might get is, eliminated by the increase in noise. So, yeah, it's waste of time. More importantly, just waste of money. It's just people trying to sell you parts you don't need. That's why I don't do them. There's no need for it. I don't need to charge people for shit they don't need. So anyhow, that was put back to stock. Now, when I do the alignment on these, because this has the Channel King board, I line it for center channel a little bit higher, because this has a lot, upper channels now. So instead of center tuning it on channel, either 1920, I'll center tune it on channel 40 to bring it up, so you have a little bit more on the top end for receive. It's still fine down low, but you have a lot more upper channels than you do lower channels. So I want to try and slant that center frequency up just a little bit to try and evenly, so you don't completely drop down to absolutely no receive by the time you get to the top end. Tied up the wires and put the cover back on the frequency counter. So yeah, that's pretty much it. Like I say, didn't have a lot of other work to do. As you heard there, I don't know if they're still on. Yeah, they're off now. Really not much skip coming in today. It's pretty much dead. Those were actually some. They're relatively local. That was non-skip. What was coming in there a minute ago. They were a good ways away from me, but I actually know some of those guys, so they're actually fairly local. So internals, only thing that's really changed up here is, like I say, receiver circuitry was put back to stock original. You see you have the original germanium diodes back in here now. The larger clear glass package with the black stripe on them. And same thing back here. You can see original germanium diodes reinstalled, and then same thing for the transistors. Transistor back here, the 2SC945 was reinstalled right there, and the factory transistor was reinstalled right there. And then Channel King board installed, so here's the PLL adapter board, and then the Channel King board standing straight up and down right here. And then the rotary encoder course, you can't see them without me tilting the radio up, but the rotary encoder and the display boards are down in there. So let me just turn her off here, and we'll actually just flip this over so you can see the bottom side now. So there are a few more wires here now. I have the power wires and the squelch wire, and then all of the other wires are run, because remember, the Channel King board has the interfaces with the microphone connector, so it takes over your receive and switching. And one advantage of doing that is, even if you're not going to use the squelch scan and, you know, like Roger Beep, Noise Toys and whatnot, one advantage of hooking that up is, this radio, normally you have to have a microphone plugged into it to have receive audio coming out of your speaker. When you install the Channel King board into any radio, you don't have to worry about that anymore. The Channel King board will supply that ground, so you don't have to worry about having a microphone jack plugged in. But yeah, so all that wiring run over to the mic jack. Like I say, reconnected the wires here, got everything tied back up. Power supply, I think I'd covered that before, about removing the board unneeded because the filter's inside the EMI filter right now. So neatened that up a little bit, and, you know, fixed the wire where it was going to get pinched through the 120 volt line. Cleaned the circuit board, installed the missing static discharge resistor on the antenna jack, and just, like I say, put in a more properly sized wire on there. It had a huge wire on there, just ridiculous in size. And that's about it. So, oh, and the clarifier, whoever had done the clarifier, I think I had also mentioned that the fine tune was just completely unhooked. I don't know what they were doing. They also had some parts removed that you really shouldn't remove. Like I guess I don't know what they were trying to do, but they goofed it up. All they had was coarse and no fine control and way too much range, quite honestly. So it's been reduced down a little bit, but it easily far exceeds the coarse control. Easily goes past 5K on either side. So, and with the Channel King board, there are no missing channels, so it covers the full spectrum now, where before I think it had like over 10 kilohertz in either direction. Just, yeah, that's just way too much. Trying to get that much slide out of a clarifier, even with a fine control, that still makes it really tricky trying to clarify somebody in when you have that much clarifier range. So, can't put the top cover back on it so you can see it because I don't have it here. Only thing the customer sent was the bottom cover, so I don't have the shielding plate or the top wooden cover to stick on it, because I told them that's just, I don't need that. It's just, you know, it's just going to cost you more to have to ship me stuff that I'm just going to have to take off anyhow and sit over on the shelf while I actually work on your radio. So alignment went fine. No, you know, surprises popped up, the receive, the transmit. I'm going to say this, it had an alignment. Yeah, I don't want to say recently, there's really no way to tell that, but it had at some point had an alignment because the transmit was just too close on to have been a factory original. At least the bias on this, the bias was within like 0.1 milliamp for both the driver and the final bias, where they've drifted off over the years. You know, because the transistors having been used, it'll change a little bit. But yeah, I'm going to say that it hadn't been screwdrivered. Somebody did an alignment on it probably at some point in time. And everything was pretty close. Like I say, the only thing that was way off was frequencies. That's because it had that crazy crystal board in here that just causes instability because all those long wires. So there you go. There's a Cobra 2000 GTL. All done, with the exception of putting only the bottom cover on this one. I'll get it put back in the box and be ready to head back to, I think this one came from the West Coast.